Welcome back. So let's look at another quadratic equation today, and just to use our the regular perturbation series formalism that we have been developing so far, and we'll also bring in the notations like the big O notation that we introduced in the last video, and sort of see how it can be used here, and in the process we'll see that we'll also have to come up and introduce a few other new notations and ideas that are quite useful and important as we proceed further in our study of perturbation methods. So let's look at the quadratic equation x square minus 2.0004x plus 0.9998 equals 0. And the reason for choosing these strange numbers is because we want to sort of cast this equation in the form of in the form of an equation where we can introduce a small parameter epsilon and then do regular perturbation methods and solve for the roots of the equation. So one of the ways we can introduce a small parameter in this equation is we see that this is something which is slightly less than 1 and this is something slightly greater than 2. So if we just define an epsilon which is so let's define an epsilon which is 0.0002 and then we can write this equation in the form x squared minus 2 1 plus epsilon x plus 1 minus epsilon equals 0, right? So in terms of this parameter epsilon, we can just recast this equation in the form of in the form of this equation, and then let's use our the regular perturbation series method that we have developed to try and solve for the roots of this equation. So what does that method involve? It involves looking for an x of the form x naught plus x1 epsilon, and in this case let's truncate it to big O epsilon square, which means we are only considering terms up to linear order in epsilon, and our goal is to solve for x naught and x1. Okay, so just like before, we'll substitute this form of a series into the equation and then compare and collect like bars of epsilon and compare them to 0. So let's do that. So first we have the x square term. This will give us x naught plus x1 epsilon square minus 2 1 plus epsilon x naught plus x1 epsilon plus 1 minus epsilon equals 0. And then if you just simplify the algebra, we'll find that so there's one very important thing. Once we have decided that we'll take the perturbation series to big O epsilon square, in all the subsequent steps we must make sure that we do not include any terms higher than epsilon to the power of 1, otherwise we'll end up getting inconsistent results. So in other words, once we have decided that okay, we'll truncate at big O epsilon square, in all the other steps we should ignore terms which are epsilon square and higher. So which means that if you're squaring this, so we have one term which is x naught square, then we have the square of this term which is x1 square epsilon square, which we'll ignore because it's of order epsilon square, which we should not keep. So but we have a cross term which is 2x naught x1 epsilon, which is linear in epsilon, so we will keep that. So 2x naught x1 epsilon, right? So these are the only two terms coming from the x square factor. And then we have this this expression which we can simplify to, let's just write it here. So it's minus 2. We have x naught plus x1 epsilon plus x naught epsilon plus x naught epsilon. That's coming from these, and then again we ignore epsilon square x1 because it's order 1, epsilon square, and then we have 1 minus epsilon plus 1 minus epsilon equals 0, right? So this entire expression on the left, I just write it again on the right side of the board so that it's not very clear. This entire expression is equal to 0. So let's just collect like powers of epsilon and rewrite it on the right side of the board to make it clear. So what are terms that are ordered epsilon square, epsilon 0 in this equation? We have x naught square minus 2x naught plus 1. X naught square minus 2x naught plus 1. And again, by generalizing the idea is that if we have a power series expansion which is equal to 0, all the coefficients of the powers of epsilon we will continue to equate to 0. So we'll find that this is 0. So that's our 0th order approximation to the roots of this equation. Now if we solve this, we find that this can be expressed in the form x naught minus 1 whole square equals 0, and that gives us x naught is 1 comma 1. So we have a double root at x naught equals to 1. Okay. What about the next order epsilon to the power of 1? So we have a term 2x naught x1, 2x naught x1, that's this one. Then we have minus 2x1, minus 2x1. Then we have minus 2x naught, minus 2x naught. And then we have minus 1 equals 0. So we have this entire expression equals 0. Now we have already solved for x naught equals 1 comma 1, and just as a reminder, the idea behind looking for a perturbative solution is that we first have a 0th order equation that we can solve exactly. Once we have the solution of the 0th order equation, we plug that into the first order equation and solve for the next coefficient, and this process proceeds systematically in this manner so that we get all the coefficients up to the order of approximation that we are interested in. So we already know x naught is 1 comma 1, which we substitute into this equation to solve for x1. So let's do that. So x naught is 1. So this term will give us 2x1. The second term is 2x1. Then again, if we have x naught equals 1, we have minus 2 minus 1 equals 0. These cancel out, and this leaves us with the equation minus 3 equals 0. And this is quite a heartbreak after all the work we've done, because obviously this equation cannot be true. So something has gone really wrong in the way we have tried to solve this equation, and now we have to figure out what is it that went wrong. Now the only possibility is that our assumption that a series expansion in this form exists. Seriously. Something is wrong in our assumption that a series expansion of this form exists. Now this is not very obvious why, but so in order to unravel what really went wrong in the way we proceeded, let's sort of step back a little bit and introduce a couple of more ideas, and then we'll systematically see where is it that we went wrong, and then then try and solve for it more consistently. So let's do that in the next part now. See you next.